Bismillahirrahmanirrahim. This is Jahangir Badar Sumar, Assistant Professor at Electrical Engineering Department, Sakkara University. In our today's video, we will discuss one of the research paper which is titled Back-to-Back HVDC Modular Multilevel Converter for Transient Voltage Dip Mitigation and Passive Networks. In my previous video, I explained this research paper, Design and Control of Modular Multilevel Converter for Voltage Mitigation. Now this work is done in 2022, and this work is totally inspired, and this work totally follows basically this work which was done in 2018. 2018. All right. This was a thesis performed by one student of bachelor's, and he worked in CERN, European Organization for Nuclear Research, for 1 year. Okay. For nuclear research laboratory like CERN, where the exceptionally high power quality conditioners are required, so there is a dynamic load. High power quality conditioners are used in CERN. The immunity against transient voltage dip is of vital importance. So if there comes the problem of voltage dip on the grid side, this is very important to mitigate that voltage dip. So the problem statement was to overcome the issue of voltage dip coming on the grid side that was affecting their load. By using the traditional HVDC MMC back-to-back configuration with properly dimensioned submodule capacitor, voltage dips can be mitigated instantaneously. So they performed the study on MMC back-to-back configuration to mitigate that issue of voltage dip, improving power quality of the network. The dimensioning of the capacitor is shown as one of the key elements of this paper, yes, because the fault right through technique applied in this paper is by using inherent energy storage capacity of the capacitors in the MMC. That energy in capacitors is basically utilized to compensate for the missing energy of the voltage dip on the grid side. Firstly, the actual voltage dip statistics recorded at CERN are presented and described. Then the traditional capacitor submodule dimensioning method present compared to proposed energy design rule. To validate the energy dimensioning and mitigation, perform a detailed Simulink model of 220 MV HVDC modular multilevel consider is described and the main results are presented. So they use MATLAB Simulink. For this study, the paper concludes with the main conclusion of this study and the future works. Okay. Today's introduction. Today, several stable solutions. There are several solutions available for voltage dip mitigation. If for smaller load, UPS can be a good solution to get uninterrupted supply. In case of dip, UPS can work better, but the limitation here is the size of energy storage, which is preferable for battery storage system, and for small systems this can work. But for higher rating, the solution of UPS is not interesting. Then researchers move towards DVR. But again, DVR is not the optimum solution. This paper suggests that the optimum solution is to, if you can afford, then the back-to-back HVDC MMC can be a good solution for mitigating voltage dip issues to deliver constant load power supply to dynamic loads. The idea of using HVDC system completely based on VSC converter to supply a high power demand with high quality was analyzed in 7, where certain operation margin allowed to take over one converter from another in case of fault. If no operation margin is kept, all converters are running at 1 per unit, then another strategy is to implement the mitigate has to be implemented to mitigate transient voltage dip. So if all the converters are running at their full capacity 1 per unit, then there need to be some fault right through strategy applied to mitigate the voltage dip, voltage sag issue occurring at the gate side. One of the solutions used by researchers in previous days was by allowing higher currents to flow during the time of transient voltage dip. A compensation effect could be attained. So if there was a voltage dip, so to compensate that missing energy of the voltage dip or voltage sag, higher current, probably 2 times more the normal current, was taken from the grid to mitigate that, to compensate that missing energy. But this is not a good solution, not recommended. This solution was investigated in research paper 8, concluding that by allowing 2 times the nominal current, a HVDC solution can protect a network from voltage dip. So they observed that if you, during the voltage dip, if you take 2 times more current than the normal current, the voltage dip issue was being solved out. Regarding the specific feature of voltage dip mitigation for HVDC links, MMC topology result the most interesting. For these converters, the electric energy stored in the capacitor which they need in any case for the normal operation can be partially used to support the voltage during transient voltage dips. So as you know that in MMC, in case of half bridge cell or full bridge cell, both topologies or every topology has a cell, capacitor cell. And one of the key characteristics of MMC is inherent energy storage capability. So that energy can be utilized to compensate for the missing energy missing energy due to the voltage dip or voltage sag. So this capacitor energy can be potentially utilized in this application. In principle, it could be expected that they provide the fast response thanks to the fast release of energy in the capacitor. The energy in the capacitor can be released fast, and it fast enough that your DC link does not go to the under voltage, and the load should not experience at all even slight disturbance. So you should release the capacitor energy very quickly, and this is possible to release it so that load may not get disturbance. This voltage dip at grid side should not affect the load. This is the objective. To explore the potential application of HVDC MMC for voltage dip mitigation purpose, an essential question is how much of capacitor energy is needed for good performance. This is the question. So now the question is, you need to know how much is the missing energy due to the voltage dip, and how much extra energy you need to store in the capacitor to mitigate that dip issue or to compensate the missing energy. How much extra energy do you need to store it? In this sense, the first decision to be made is to choose between the transient voltage dip mitigation strategies and increasing line current strategy and an energy storage based solution. So there are two approaches. One approach to mitigate that voltage dip strategy is the increasing line current strategy, which is not good, because if you are using increasing line current strategy, then the higher currents 2 times more than normal current will flow. In that case, the converter size will be overrated, converter station will be more costly, having more footprint weight. So this is not recommended. The recommended approach here in this paper is the energy storage based solution. But now researchers are working that even the best choices, that your controller's design should be such effective that neither we should prefer this line current strategy or energy based storage system, but there should be automatic switching. The controller should be fast enough and robust enough to mitigate this issue. So researchers are also working in this area. Anyhow, in this paper, the technique suggested is energy storage based solution. We will discuss energy storage based solution. The first storage strategy is allowing the rectifier to draw increased current during the voltage dips such that the DC bus transfer nominal power at all times. With the inverter synthesizing AC voltage for the load, applying this solution with MMC means the semiconductor switching devices and sub-module capacitor must be highly overrated compared to required rating for normal operating condition, the rectifier, making the solution less elegant and interesting. Therefore, increasing line current stage is not good enough because it will increase the overall converter station size, cost. The second study, which is the one proposed in this paper, is to design the MMC sub-module capacitors according to dedicated energy calculation presented in the energy calculation chapter. The rectifier shall be designed to draw nominal current from the grid during a transient voltage dip, extracting the maximum allowed power to optimize the needed storage for dip mitigation. The advantage is that both rectifier and inverter will be dimensioned for normal operation condition, and by using proposed design method for the overall system design optimum is reached. So this is better approach to use that capacitor energy storage property to mitigate this dip. In general, the MMC show very high efficiency and provide several power quality conditioning features to passive networks such as voltage dip mitigation, reactive power compensation. So reactive power compensation is also possible with MMC-based HVDC system. A passive network in this synopsis in the paper is defined as a network with a short circuit ratio of 0, which means no generation of energy. Okay. Behind acting as a dip mitigation, the inverter can provide reactive power support for the passive load network in 2 quadrants and even supporting pulsating dynamic loads. So this is additional advantage that reactive power support to the load is also possible with reactive power controller on the inverter side. In the case of particle excess, this could be very beneficial feature for it could replace static VR compensator. So no need of a static VR compensator in this case. If you have back-to-back HVDC MMC system, the rectifier has ability to support the grid with reactive power injection during faults and can allow power oscillation damping grid stabilization. Lastly, the system features steady state control allowing high precision of voltage and frequency regulation for the passive network. So even during this voltage dip, there will be no effect on the load. The load will be getting the constant power supply. There will be no disturbance on the load side. This paper is in general analysis of the potential of transient voltage dip mitigation of an MMC-based HVDC back-to-back line link. An important part is the dimensioning of the capacitors. So this is very important. Analyze an energy dimensioning chapter, which highlights also the correlation between storage size and dip mitigation performance. So certainly, the storage size capacitor dimensioning will depend upon what is the dip severity, how much dip is happening for how many seconds, how much amplitude of dip is there, depending upon the dip severity, amplitude of the dip, time of the dip, capacitor dimensioning will be performed, energy storage size will be performed. And this is performed in detail in the thesis work of this same author. You can also refer to that thesis of this author. After the main simulation model is present, including also the control circuit, the conclusion shows the main result concerning dip mitigation performance. Okay, the energy dimensioning, which is very important because it uses capacitor energy storage property. So energy dimensioning of capacitor becomes important. The target of this paper is to show the potential of MMC-based HVDC link system for transient voltage dip mitigation and give insight in energy storage calculation for the modules. This will mean a new proposed design rule for MMC converter when transient voltage dip mitigation is required. The traditional way for storage design in the module, which is done in the industry, is to design the energy storage of MMC converter around 30 to 40 kilojoule per MVA. So converter station traditional way of storage design is that range is 30 to 40 kilojoule per MVA per converter station. For a back-to-back system, this results in a total system energy because one is the rectifier station, other is inverter. So total system energy is of 60 to 80 kilojoule per MVA. But with the object of dip mitigation, a new design for the value of stored energy per MVA has to be derived because this is for the normal case. But if you want to mitigate the voltage dip without taking increased line current strategies, then this need to be recalculated. The first step is to analyze the discharge capabilities of submodule capacitors. As the modular multi-level converter is assumed to operate with a DC voltage of 1 per unit, so the requirement is that you need to maintain DC voltage 1 per unit, means whatever the desired reference voltage is, that should be tracked. In per unit, it should be 1 per unit. At modulation index of 0.8 in a steady state. So in a steady state, modulation index value preferred is 0.8. The inverter is limited to minimum DC voltage input of 0.8 per unit. That means DC link should not fall below 0.8 per unit. If it falls below the 0.8, if it becomes 0.4, 0.5 per unit, then the inverter has to operate in hour modulation, which is not required, which is a big problem. Hour modulation is an issue, and if there comes opposite problem, not the under voltage, but our voltage in the DC link, that is also issue. That will burn the equipment, burn the DC cable, our MMC station, MMC converter station and HVDC can collapse. So both under voltage and our voltage in the DC link are not desired. The total energy stored for both inverter and rectifier depends on DC voltage of the bus. The following is the fundamental equation for energy in the capacitor. This is a well-known equation of energy stored in the capacitor 1/2 CV square. With this in mind, the total energy stored must be high, that after mitigating a dip, the DC voltage should not be below 0.8 per unit based on the previous equation. So we have to make sure that capacitor discharges the energy fast enough so that DC voltage should not fall below 0.8. This means that capacitors are only allowed to discharge up to 36% of their initial steady state charge. This result concludes the total energy of the capacitor should be damaged 2.77 times the missing energy for the inverter operating with modulation index of 0.8. Means if the missing energy, whatever the missing energy is divided by 0.36, this means the energy stored in the capacitor should be 2.77 times more than the missing energy. What? Calculate the missing energy due to the voltage dip, and then you should store 2.77 times more as compared to E missing multiplied by E missing. So let's say if E missing is 0.3, then E stored should be 2.77 into 0.3. Second step is to find the missing energy of system caused by the dip. So a statistical analysis of all mild voltage dip in a highly sensitive distribution is present in figure 1. This shows that this picture shows voltage dip magnitude percentage, and for the time, how much time the dip remains. And accordingly, depending upon this curve, we will come to know that how much energy need to be stored in a back-to-back HVDC MMC system. Okay. Then a function called dip severity is introduced. Dip severity, this function is the dip magnitude multiplied by dip duration. If the dip duration, let us say if it is for 75 millisecond, and the dip magnitude is 50%, so 50% multiplied by multiplied by 75 millisecond will be the dip severity. So if you multiply both dip duration with the dip magnitude, you will get dip severity, where dips are assumed by three-phase dips. The calculation operates in per unit system with 1 second as per unit in time. This makes power energy base equal. Figure 2a shows histogram of dip severity for all required dips, and logistic distribution function is fitted to data. As it can be observed, majority of register voltage dips are included in a window of 50% at 150 millisecond. So figure 2a, the data was collected. It was observed that the most repeated pattern of the dip severity was 50% dip for 150 millisecond in the sun network. Figure 2b shows distribution density function rate and the cumulative function. The cumulative function essentially shows how to dimension the stored energy of the converter as a function of confidence, with 99% being the chosen value for the study. More trivially explained, a 99% confidence translates to 99% of all voltage dips will be mitigated. So in this research paper, the capacitor dimensioning or energy dimensioning is made not 60 to 80 kilojoule per MeV, because this is for the normal case, but for voltage dip, this needs to be recalculated. So it is designed for such a value so that 99% of dips are successfully mitigated. The fact that rectifier will always draw nominal current from the grid means that dip severity is in the fact missing energy caused by the dip. So E missing is current dip, change in current dip multiplied by change in V dip multiplied by time in T dip, how much time dip lasts. By graphical solution of our 99% confidence figure 2b, the missing energy is seen as 0.0375 per unit. So if you see here, so the missing energy due to the dip in the sun network with that particular load was missing energy in most of the time, 99% of the time was 0.0375 per unit. This was the missing energy due to the dip. So if this is the missing energy, now how much energy should be stored in the capacitors? It should be, E stored should be 2.77 times this missing energy. So multiply 2.77 with this value, you will get that total stored energy should be 0.104 per unit of the system, for the system. assuming a system of 1 MVA rating, this means that the rectifier and inverter together must have an energy of 104. 0.104 means it should have energy of 104 kilojoule per MVA. Normally it is 60 to 80 kilojoule per MVA, but for the mitigation of voltage dip and for compensating the missing energy and to make sure the 99% of the voltage dip severities are successfully mitigated, the system should be now having energy storage of 104 kilojoule per MVA. Now this is the disadvantage, that overall energy dimensioning is changing. Overall capacitor sizing will be different. So this will make this converter station little bit expensive as compared to normal. So this approach has the disadvantage in terms of cost. Comparing this result with the commonly used 60 to 80 kilojoule per minute shows by only a slight increase of stored energy. So there is a slight increase. Normally it is 80 kilojoule per MVA, but to mitigate the voltage dip, the system should be 104 kilojoule per MVA. 99% all volt dips will be mitigated if the system is of 104 kilojoule per MVA. Energy storage is this one. Okay. So in the next part, we will discuss simulation model and the results. Thank you.